All right. Hi, everyone. Thanks for coming today. This is going to be actually the last talk of the semester. Today, our speaker is Keegan Harris, who's a PhD student in computer science at CNU. And he's been working on machine learning, algorithmic game theory, econometrics, and the intersection of those different fields. He's also advised by Nina Balkan and Stephen Wu. And today he's going to be telling us about his work on algorithmic decision making under incentive, Apple tasting feedback, and multi-class learnability. So it's all you now. Again, go ahead.
Great. Thanks for the introduction. Yeah, I'm excited to be here. And if anyone has any questions, feel free to stop me along the way or things you want me to clarify. And yeah, this is joint work with some pretty great collaborators, Anish Agarwal, who's starting faculty at Columbia soon, Hara Bodhimata, who's starting faculty at MIT soon, and Stephen, who's my co-advisor at CMU. And this work is based largely on two working papers. The first one's called Strategic Apple Tasting with Hara and Stephen. It's not online yet, but I promise it will be very soon. And if anyone wants a copy, feel free just to email me. And the second part of the talk is based on this preprint I have with Anish, Hara, and Stephen called Strategy Proof Decision Making in Panel Data Settings and Beyond, which is online now. And in particular, today, I'll be focusing on sort of the main results of the Strategic Apple Tasting paper and the and beyond results of the panel data paper. So I'm sure many people here know that machine learning algorithms are used increasingly to assess individuals' qualifications in many high stakes domains, including areas such as lending and employment. So, as just an example for lending, you can imagine a loan applicant comes to a bank and says, "I'd like a loan." The bank says, "Tell me about yourself." The applicant gives it some set of observable features, such as their credit history, their incomes, the number of credit cards, et cetera, et cetera. And then, the bank goes to their machine learning model, their algorithm says, "What do you think?" The algorithm or model says yes or no. Ideally, it'll also say why. And then using this information, the bank makes their own decision and says yes or no. Similarly, in hiring, you have an applicant come to a company, says, "I'd like a job." The company says, "Tell me about yourself." They give it information such as previous work experience, reference letters, skills, et cetera, et cetera. The company goes to their machine learning model, their algorithm says, "What do you think?" It says yes or no, and the company uses this information to help inform their decision about whether or not to hire this person. And this raises several concerns. The first of which might be transparency. You want these machine learning models, these algorithms that are being used to help inform decisions, to be transparent and explainable. Also, another thing everyone here cares about is fairness. You want these models to not disproportionately negatively affect certain subpopulations over others or individuals over others. And another thing people would care about are the so-called downstream implications of using machine learning in these settings. So, what effects does this have on the population that is being scored? And this will be the primary focus of my talk today. But, as you can imagine, these three areas are sort of deeply intertwined, and I hope you'll see some of that coming through today. In particular, the type of downstream application I'll be looking at in response to these machine learning models is that of strategic responses. So in particular, when machine learning models are being used to make decisions about individuals that care about the outcome of the decision. So, these individuals are applying for a loan because they want one, they're applying for a job because they want one. Then these individuals have a game theoretic incentive to modify the information that they give to the algorithm. And, this isn't just something studied in theory, this is something you actually see in practice. Like a quick Google search gave, actually I'm at Microsoft now, so I should say a quick Bing search gave, lots of articles like how to improve your credit fast. And, some of these are things such as pay bills on time, which is generally good advice that does help you become more quote unquote credit worthy. But other things are, things is number one, where they tell you to pay credit card balances strategically, which doesn't necessarily have an effect on your credit worthiness and is just in some sense trying to game the system. Similarly, for hiring, You see articles like, lists of resume keywords to list on your resume to pass some automated screening software. And there's even a subreddit called Job Search Hacks, and with posts such as, is it a good or bad idea to put like certain keywords in white font on your resume to pass some of this automated screening software. And so I guess let's concretize this a bit. We consider a game between a principal or a decision maker and a strategic agent or a sequence of strategic agents, but let's just focus on one right now. So in this game, the principal moves first. They deploy some policy, and all a policy is a mapping from observable features to decisions. So accept or reject the loan, for example. With this in mind, the strategic agent wants to optimize the prediction or decision that they receive. So they're going to sort of strategically modify their features that they give to the principal to be scored by the policy. And under this setup, the principal can have one of several goals. So one goal you might be interested in is like sort of societal concerns, where you want to incentivize like desirable feature improvements that are somehow beneficial. Another area which has gained recent interest is that of causal learning in this setting. So, you may just want to learn the causal relationship between observable features and outcomes, which is now harder because these features are strategically modified. Or you might also want to learn which modifications actually improve and which ones are just sort of gaming. But maybe the most basic goal, and the one I'll be focusing on today, is just getting accurate predictions in making right decisions in the presence of this strategic behavior. So this is now a long line of work along this area, broadly under the name of strategic classification or strategic learning. And the original paper was by, I think, Part et al. In 2016. And recently there's been some work that looks at this in sort of an online setting with causal implications in mind, with repeated interactions between the principal and like the same agent over time, as well as in like various social learning settings, and many more that I couldn't fit on the slide. So our specific model that we'll be looking at today considers an online learning setup where agents arrive one at a time sequentially in order to have a decision made about them, and then they go away forever. And so this sort of ignores the effects of repeated interactions, which I guess is important, but it's not what we'll be focusing on today. So specifically, at each time t, the principal deploys some policy pi t, which recall is a mapping from observable features to outcomes. At the same time, a new agent shows up with observable features, I guess, with features xt. So these are, I guess, private to the agent for now. The policy doesn't know it. Knowledge of this policy causes the agent to take some action which modifies their features from xt to xt prime. These modified features are then reported to the principal. And then, given these modified features, the principal makes a decision about the agent using the policy that they said they would. And then, the hope and the goal is that the feedback that you get at this time is going to be used to improve the policy at the next time. But I guess the point of the first part of the talk is to take a step back and ask, what type of feedback does the principal actually receive? So full feedback, where after every time step they get to see the quote unquote true label of the individual being scored, I would argue is too restrictive. In the hiring setting, that would correspond to getting to see whether or not the employee was good, or whether or not the applicant would have been a good employee had you not hired them, and seeing whether or not a person would have paid back a loan if you decided not to give them one. Which, in practice, you don't get to observe either of those things. So instead, what we do is we argue that this apple tasting feedback is a more realistic model of the feedback you receive in such settings. So I guess, what is apple tasting feedback? The idea is that you only receive feedback when a positive classification is made. And the intuition is you only know how the apple tastes if you decide to taste it. So I guess at least heuristically, the idea for this comes from you have an apple in front of you and you want to predict whether it tastes good or bad. If you predict it tastes good, you taste the apple and you see if it does taste good or bad. If you predict that the apple tastes bad, though, you don't taste it and then you never get to see how it actually tasted. And the original paper on this, actually, I think this might be the journal version, is by Nick Littlestone and co-authors around the year 2000. And they looked at online classification with apple tasting feedback. However, recently, there's been some work on apple tasting feedback in areas such as algorithmic fairness and recidivism prediction, which may be of interest to people on the call. Actually, I think we may even have some authors on the call of some of these papers. So the model we consider is that of a cost-sensitive linear classification problem with apple tasting feedback. Specifically, we assume that there's some constant reward for assigning a negative classification. So you just think of the principal as getting zero utility from a particular agent if you decide not to offer them the job, or if you decide not to offer them the loan. However, there can be some variable reward if you decide to offer them the job. They could be a superstar employee, or they could do like really bad and you have to fire them. So there's a wide spectrum of rewards you get from that. And we capture this via a linear relationship with the original unmodified features that the principal does not get to see. So this is some unknown relationship theta between the original features X and maybe there's some random noise due to inherent randomness or measurement error or whatever. And crucially, we have apple tasting feedback, so we only see this positive reward whenever a positive decision is made. And so we need to make some assumption on how these agents strategize. So we assume that they can modify their observable features anywhere within some bounded L2 norm of their original features. And you might see this in the literature on strategic classification under the name of a effort budget. And it represents like a hard constraint on the amount of effort that you can spend to modify your features. For instance, maybe you have a certain amount of time or a certain monetary budget to modification. And I guess another assumption we'll make here, which we will revisit later, is that of quote unquote lazy tie breaking, which basically says individuals don't modify more than they need to. And so our performance metric in this setting is strategic regret, which compares the performance of the sequence of policies that the principal deploys in an online fashion to the optimal and hindsight policy, which works on non-strategic agents. So mathematically, what that's saying is here on the left, you have the cumulative sum of the rewards for the optimal policy that gets to see the unmodified features. And you're comparing that to the total reward for what you did, which is the sequence of policies pi t, which has to act on the modified features. And our goal is to get a no regret algorithm on average, as the number of agents t grows large. So if your strategic regret divided by t, if that goes to 0 and the limit as t goes to infinity, that means that your performance is approaching the performance of sort of the optimal thing to do, even in this non-strategic setting. And that's our goal. Okay, so I guess any questions about the setup? Cool. So if not, let's get into some of the characteristics of the offline optimal solution. So if you knew everything, so I guess we're trying to ask the question, if you knew everything about the problem, what would you do in order to account for the strategic behavior? And so one natural thing to do is to construct a separating hyperplane, which separates all the agents who should receive a negative classification from all those that receive a positive classification. And you're constructing this hyperplane in the observable feature space. So for instance, maybe it's this blue line here. So if agents were not strategic, maybe the optimal thing to do would be to assign action 0, aka negative classification, to all the agents to the left, and then action 1, or a positive classification, to all agents on the right. And then what you're going to do is you're going to take this decision boundary and you're going to shift it by some amount delta in order to account for the fact that agents strategize and they have this effort budget of size delta. And so what that does is two things. One, it makes it so that no agent who should receive intervention 0 needs to strategize. Or sorry, no agent that should receive action 0 can receive action 1 by strategizing, because they can only move delta, so they can't move far enough to get it. And it ensures that all individuals who should receive action 1 can do so, although now they may need to strategize in order to receive it. Okay, so our main result for apple tasting feedback is this sort of greedy algorithm, where the basic idea is we're going to keep an empirical estimate of this optimal shifted hyperplane, and we're going to play greedily with respect to this. And the hope is that if your agent population is sufficiently diverse, like you'll be performing sort of implicit exploration, and you'll have no need for any explicit exploration, and this will result in sublinear regret. And I guess as an aside, there's been work in the contextual bandit literature which shows that greedy algorithms often perform well in practice. And there's also been a recent line of work which attempts to explain this phenomenon in non-strategic contextual bandit settings. So basically what this boils down to is sufficient conditions on like diversity in, I guess in the contextual bandit case, it would be on the population of contexts under which greedy algorithms work well. So I guess let's get into what our algorithm looks like. So it's sort of like a warm starting step. We assign action 1, this action which we receive full feedback on, for the first D rounds, where D is like the dimension of your feature vector. And you collect some data set. You just observe the observable feature reward pairs that you get. And note that we're assigning actions deterministically here, so individuals don't have an incentive to modify. So then for the rest of the time, what you do is you estimate this true relationship data between observable features and outcomes as some theta hat using, say, ordinary least squares. And you can do this because I guess an invariant that we're going to maintain is that none of the data that we use to do this OLS estimation has been strategically modified. We want to guarantee this invariant over time. So then, we have to commit to our policy. So we're going to assign action 1, which is the positive action, if and only if. So essentially, if and only if we are on this side of our estimated shifted hyperplane. So that's all this says. This is the inner product between your modified observable features and your best guess of theta. This is a term, I guess also, I hope you can see my mouse. But this term right here is some shifted amount to account for the strategic manipulation. And this R0, you can think of it as 0. It's just the constant reward you get for assigning a negative classification. And then, we want to maintain our invariant of only updating this theta estimate on, I guess, quote unquote, clean data, data we can guarantee has not been strategically modified. So I guess recall that under lazy tie breaking, if an individual modifies, they're going to modify as little as they need to. So they're only going to modify like up until the decision boundary. So if they have observable features that fall strictly on the other side of the decision boundary, so strictly in this triangle up here, not on the boundary, then we can infer that these features have not been modified, and we can add this point to our data set. And we can use this in future rounds to update our estimate of theta. On the other hand, if this condition is not satisfied, then we can't make any guarantees that the data hasn't been modified, and so we don't use it to update our data set. And so the theorem is that essentially what it says, is if the agent population is sufficiently diverse, and by sufficiently diverse, we mean the distribution over agents has some bounded density ratio with the uniform distribution over the unit sphere, then the regret we get is sublinear in T. Specifically, we get square root t regret, where recall t is the number of agents. I guess we also have this curious looking term out in front where delta is your effort budget and d is the dimension of your feature vector, but we'll return to this shortly. So I guess that's sort of the main result of this part of the talk. And now we'll get into some extensions. So the first extension is, you might say, hey, it's unrealistic that these individuals modify, like are completely lazy, like maybe they don't best respond exactly to the decision boundary. Maybe they sort of overshoot it sometimes. And this could be due to, for example, bounded rationality or like imperfect knowledge about the policy, or just being like risk adverse and like wanting to be safe that they get the positive decision. So yeah, like I said, we allow for agents to overshoot the boundary by some amount at most gamma. I guess the amount each individual overshoots can be arbitrary, but we, I guess, importantly need to know it's bounded. And then the idea is that we can modify the algorithm to only count contexts as clean or unmodified if they are now gamma away from the decision boundary, instead of just strictly lying on one side of it. And so what will happen there is
Keegan,
we'll pay.
Can I ask a quick question for intuition? Maybe you're going to get
Sure.
to it. So I think I understand the general gist of the algorithm. And I guess, right, you need this diversity smoothness assumption because you're using the greedy algorithm rather than something that explicitly explores.
Yeah.
But I don't understand why you need to use the greedy algorithm as opposed to lin UCB or something. Like if I understand, there's sort of this trick of using only points that you can certify didn't get strategically modified if they're sufficiently across the linear boundary, but you could have done that without, like, why do you need the greedy algorithm?
Sure, yeah, that's a good question. And I guess it's sort of this, this, I guess, nicely ties into this theme of interpretability and explainability when making decisions with algorithms. Because I guess from both a theoretical point of view and a practical point of view, how would you model someone as best responding to, say, lin UCB? It's like this highly nonlinear policy. Like if you told me you were making decisions about me using like lin UCB, I guess I personally would not know how to.
But like lin UCB also deploys a linear policy at every round, right? Like I could announce it. I could be like, this is the linear hyperplane I'm using today.
Yeah, but I guess it's it's optimistic based off of the observable features that you present. No, like, right? Like,
oh, okay. I see. So you're saying actually it's linear only conditional on the features you present. So actually it's
exactly.
nonlinear.
Yeah.
Got it. Okay. Thanks.
Yep. Yeah. So I guess maybe from a theoretical point of view, that's the motivation for using like a greedy algorithm. And then also you have, I guess, the practical point of view, which is that you would hope that the distribution over agents in some of these motivating examples is sufficiently diverse for this to work well. Yeah. Okay, yeah. And yeah, so I guess like I said, you can allow for this overshooting, this sort of trembling hand best response and only pay like, I guess, only pay an additional factor of minus gamma in this this constant term right here, which, as you may notice, is exponentially large in the dimension of the observable features, which may not be the best, right? So that is the second extension. So in settings where you have an extremely large number of agents, such as you're, maybe deciding to hiring people at a very large company, or you're, like a large bank that has many loan applicants, this might be okay, because the large T will dominate out this large constant. But, maybe maybe you work at a small company that only gets a couple new applicants every year. So in this case, this constant may be prohibitively large. So if I guess, this time horizon, this number of agents, then you can use a variant of what's called the explore then commit algorithm, which is, I guess, this sort of fundamental idea in bandits where basically you explore for some certain amount of time, and then you sort of get some estimates, and then you commit to the best thing so far. And so in our case, what that would look like is you would explore by assigning the positive action, because that's when you get feedback. And then you would commit to sort of your best guess of the shifted hyperplane. And if you do this, you would get linear in the dimension, but a worse dependence on the number of agents. So this is t to the 2/3 now. And yeah, so if you knew the time horizon, you could just sort of like pick, what's the best of these two algorithms to do. You compute the regret upper bound and do that. But what if the time horizon is not known? So for basically, there's like some inflection point where it becomes more beneficial to use this a strategy-aware version of OLS as opposed to this explore then commit. So what you can do in this setting is, if you don't know the time, you can play explore then commit with a doubling trick. And then if you don't know what a doubling trick is, it's sort of this like classic idea in multi-arm bandits where you want to restart the algorithm with, I guess, exponentially longer run times each time. And you do this whenever you don't know the time horizon, and this gets, I guess, the same performance as the algorithm if you did know the time horizon up to like constant factors. So you do this explore then commit with like some doubling trick up to a certain time, and then you switch to ordinarily squares, or at least the strategy aware version. And what this gets you is sort of the best of both worlds. So it's on the order of the minimum of the two regrets. So on the left here, you have this root t regret bound with this perhaps undesirable dependence on this constant. And then you have this bound over here, which is slightly worse than the number of agents to the 2/3, but it has like this linear dependence on the dimension of the context. And you can get, sort of the best of either one with this procedure. Okay, so then another extension, I guess this is more theoretically driven, is what if you don't buy the story that the actions or the agents are sufficiently diverse? What if you say, okay, like, how can I handle adversarially chosen agents? And so one idea here is play exp3, which is this classic bandit algorithm over some discretized policy grid. And this gets you sublinear regret, but it does come with its drawbacks. So the first drawback is that the regret bound isn't very good. It's like t to the d+1 over d+2, which is the classic rate you get for like discretizing some continuous space. And I guess another downside of this is, you get an exponential runtime because the grid that you need to have over these discretized policies is exponentially large in the dimension. So I guess the important open question I think we have here is, can we do better in this setting where these agents are adversarially chosen? And I guess I just want to clarify that by adversarially chosen agents, we're still assuming that this linear relationship, this linear relationship here holds, but now we're making no restrictions on the context generating process, the observable feature generating process, which generates a sequence of X's. Okay, and then the fourth extension, which I'll just mention briefly, is all of our results that I presented here extend to the more broader setting where you have bandit feedback. So now the feedback for a negative decision is not constant for whatever reason. It can, it's also some linear function of the unmodified observable features. And we can handle that too with just like very slight tweaks to the algorithms. Okay, so I guess maybe now would be a good time to stop for questions, if there are any, because this is like sort of the end of the first part of the talk and the beginning of the second part.
Maybe like a boring technical question. But you said your sort of diversity smoothness condition was that you're, like not too far from your probability densities are sort of bounded away from a uniform distribution.
Close to a uniform distribution.
Bounded, close to a uniform distribution. which is, I guess, like a stronger condition than you need for the greedy algorithm to work in like the usual contextual bandit setting. You can get results where you just, you know, the adversary can choose arbitrary points and then they're just perturbed with sort of, is there a good reason you need that stronger condition, or is it just easier?
Yeah, I guess it's just easier. That is something that I'm looking into now, though, is if we can handle this this adversarial, I guess, corruption or adversarial choice, and then sort of like smooth it with random noise. Yeah, I guess intuitively, I think it will work, but probably is like a lot harder to analyze.
Got it. Thanks.
Okay, cool. So I guess if there are no more questions, we can move on to the second part, which is about multi-class learnability in strategic settings. So, you know, in particular, there's no need to restrict ourselves to binary classification. You can imagine that strategic interaction may also arise in multi-class settings. So one example of this is assigning discounts to users. So suppose you have several levels of discount, you know, 10%, 20%, 30%, etc. You know, 0% discount. And, you know, of course, users, if it's like some online platform, Amazon will prefer higher discounts to lower discounts. So they're going to want to strategize in order to get the highest discount they possibly can. However, you know, the platform would only want to give individuals the discount that they quote unquote need, you know, whether this is like, you know, maximize revenue, or maybe this is a government agency that has some limited budget for assigning discounts to people who need them. So, you know, like these people down here, they don't have a lot in their cart. So maybe you want to incentivize them to spend more, so you give them a higher discount. Whereas this guy over here has a lot in his cart, so he doesn't need a discount in order to buy a lot, and you know, and you want to be able to predict that. So the question is that in settings like this, can we design strategy for policies as well? And by a strategy group policy, I mean the policy that assigns the quote unquote correct action to all strategic agents. And by correct, I mean the action which maximizes the reward of the principal. And the answer, perhaps surprisingly, is not always. And I will give a condition for when you can and can't. Okay, so I guess to get some intuition, let's go back to our two action setting. And in particular, the idea of constructing a separating hyperplane between individuals who should receive action 1 and individuals who should receive action 2, and then shifting it to account for strategic behavior. So recall we had this image here where if agents were non-strategic, this might be the optimal decision boundary to do or to deploy. But now since they're strategic, we shift it by some amount delta. And you know, your first guess is maybe we can apply the same logic to this setting with 3 or more actions. So I guess now I'll show you a quote unquote bad example where this is not possible. So suppose now you have 3 actions, actions 0, 1, and 2, and individuals prefer action 2 to action 1 and 0. And let's just say for simplicity that they're indifferent between actions 1 and 0. But you know, this doesn't need to hold. And suppose that if agents were not strategic, these sequence of blue separating hyperplanes would be sort of the optimal thing to do. So now let's, you know, port this to our strategic setting. What we want to do is shift in the decision boundary by some amount delta to account for the strategic manipulations. And what this does is this ensures that individuals who are strategic and are not of type 2 cannot receive type 2. But what you've done, if you know, depending on this angle here, is now made it infeasible for an individual who say is you know, at the very corner here, who should receive type 2, who needs to strategize. Now they cannot receive it actually, because this distance here is strictly greater than delta. Okay, so I guess this is the intuition, but we can formalize this example. So in particular, we can give a necessary insufficient condition under which, I guess, designing a strategy-proof intervention policy is possible. But in order to do that, we need to introduce a couple definitions. The first of which is agent type. So we say that some agent T is of type A, where A is one of your actions, if this action is the action which maximizes the reward of the principal. So in this example here, all individuals in this 0 block would be of type 0. All individuals in this 1 block would be of type 1, and all individuals in this 2 block would be of type 2. And another definition we need is a notion of a best response ball. And this can be either for an individual agent or for some arbitrary set of agents. And we say that a best response ball is the set of all modified observable features that are quote unquote reachable by at least one agent in the set. And by reachable, I mean can be modified to under the effort budget assumption. And so what this looks like is consider this set of units, agents rather, let's call this set of agents U0, and they are in this dotted circle. Their best response ball would be all possible sets of observable features that can be reached by them. So essentially you're going to expand this ball of observable features by some amount delta, and that is the amount reachable, and that is the, I guess, best response ball for that set of units, set of agents in the dotted circle. So does the idea of a best response ball make sense? Cool. Okay, so I guess furthermore, we're going to assume that these actions are ordered in increasing order of agent preference. So we're going to assume that agents prefer action 1 to action 2, action 2 to action 1, etc. And an easy example to keep in mind is just like this discounting thing, where people prefer higher discounts to lower ones. Okay, and our necessary and sufficient condition, we're now ready to introduce it, is called separation of types. And in particular, separation of types says that there does not exist an agent of type A whose best response ball for that particular agent is a complete subset of the union of best response balls for agents who have type less than A, so who should receive some intervention less desirable than A. And mathematically, what that looks like is the following, so just to walk through this again, for all possible actions, there does not exist a individual who, I guess, is of type A. We're denoting that by U of A, such that that individual's best response ball is not a complete subset of the union of the best response balls for actions of number less than the action that type A is of. And so I guess maybe the best way to get some intuition for this condition is via an example. So here's an example of a setting in which separation of types is not satisfied. So you have 3 sets of individuals, individuals who should receive action 0, and they're in pink here. I guess they're within the dotted line circle, and their best response ball is the thing in pink. Likewise, you have individuals who should receive action 1, they're in the green dotted circle. And then you have individuals who should receive action 2. They're in the yellow dotted circle. And we're assuming that action 2 is more desirable to individuals than actions 1 or 0. So naturally, the individuals that are of type 0 or 1 are going to try to strategize to receive action 2. And so here, separation of types is not satisfied because this individual here, this black dot, their best response ball is denoted by this slightly darker yellow circle. And you'll notice that this is completely contained in the best response balls of units of type 0 and units of type 1. So what this means is that no matter how they strategize, their observable features can be matched by some unit of a lesser type by strategically modifying. And importantly, these units or these individuals of a lower type have incentive to do this because they want to receive the same intervention that this individual of type 2 is receiving. So an example of a setting where separation of types is satisfied is essentially the same picture, but now the set of individuals who should receive intervention 2 or action 2 are slightly elevated. So now you don't run into that same situation where you have an individual on the boundary whose best response ball is completely enclosed in other individuals' best response balls. Okay, so then the theorem is that a strategy-proof policy exists if and only if separation of types is satisfied. And I guess just to give you the proof idea, we have, I guess, two sides of the coin. The first side is that if separation of types holds, a feasible policy can be obtained by using this like shifting idea that we use in a 2-action setting. So, like write down the separating hyperplanes and shift them some amount to account for a strategic behavior, like as in this case. So, like the separating hyperplanes in this case are very similar to the example I showed. You have one down the middle and then 2 on the sides, but now you can shift the upper 2 a bit to account for the strategic behavior. But without separation of types, then there will always exist at least one agent that cannot be quote unquote separated from the agents of lower types under any deterministic policy. So, I have a situation like this where no matter how this individual in dark black strategizes, their observable features can always be obtained by either an agent of type 0 or an agent of type 1. And as like a corollary, or I guess the way I presented things is like a sanity check rather, the separation of types condition is always satisfied when the number of actions equals 2. So now we're back in the binary strategic classification setting under this linear setting that I presented in the first half of the talk. So I guess a couple implications of this. One thing that's interesting is, this doesn't appear just to be like some weird edge case. And, this is not a result about actually like learning. It's a result about, just like the structure, whether this thing exists or not. So it's independent of the feedback you get. You get full feedback or some type of like bandit or apple tasting feedback. This impossibility result still holds. And what this implies is that in the online setting, sublinear strategic regret is not possible because the optima in hindsight on strategic individuals is strictly worse than the optima in hindsight on non-strategic individuals when separation of types does not hold. And I also think this could have some interesting implications for fairness because since you can't do perfect classification in the strategic setting anymore, maybe there are some trade-offs you have to make, some decisions you have to make between trading off between false positives and false negatives under strategic modifications. And I guess, the one thing I didn't mention is that the main point of this paper, which is the second one, the one with Anish, Hara, and Steven, is like this panel data setting, which is a setting which is commonly studied in causal inference. I didn't get into any of that. This is sort of just a technical result we use to prove stuff along the way in that setting. So if you're interested in sort of strategic interactions in this like richer data collection setting, I'd encourage you to check out that paper. So I guess before I conclude, does anyone have any questions? Cool. So if not, I hope I've convinced you, or maybe you were already convinced before you came here, that it's important to design strategy-aware classifiers when you're making decisions or you're using them to aid in decision making in like real-world settings of importance, such as lending, hiring, et cetera, et cetera. So for the 2-action setting, we focused on this apple tasting feedback, where you only receive feedback about the decision you made when you make a positive decision. And our main result was this strategy-aware greedy algorithm, which achieved square root t regret when the distribution over agents was sufficiently diverse. And by sufficiently diverse, I mean, having a bounded density ratio with the uniform distribution. We also talked briefly about extensions to so-called trembling hand best response, where maybe they don't lazily best respond exactly. They could overshoot it by some bounded amount. We talked about the setting where you don't know the number of agents you need to make decisions about. So recall there, what you might want to do is this explore then commit with a doubling trick until some time where you switch to the first algorithm. And then we talked about adversarially chosen agents, where not making this assumption, what can we do if the choice of agent observable features is arbitrary? And then I guess I didn't really show you, but I alluded to the fact that our results also extend to when you have bandit feedback. So now the feedback for a negative decision is not just always constant. It can vary just like for the positive one. So for three or more actions, we showed a possibility result for making decisions using deterministic policies. And this is for the offline setting, but it immediately implies that in some settings you can't achieve no strategic regret. Like I said, there's some extensions to this panel data setting, which may be interesting to people. And you need to consider the trade-offs between like these false positives and false negatives in settings under which the separation of types is not satisfied. Which could have some like interesting implications down the line. So for future work, for two actions, I think it would be interesting to sort of look at like lower bounds for this. I guess I call it price of manipulation. This 1 minus delta to the d term, which depends on I guess both the dimension of the feature vector and then also the ability of an agent to modify. Is this large constant really necessary? Can we remove it with either a different algorithm or a different analysis? I'm pretty sure you can't remove it with a different analysis, but maybe there's a different algorithm you can use. And likewise, like for the adversarially chosen agents, can we get a better regret bound than the one we currently have? For three or more actions, I think there's some interesting implications of this impossibility result, perhaps in the context of fairness. And when the separation of types doesn't hold, I think it's actually interesting and non-trivial to characterize the form of the optimal policy. And if you could characterize that form, then you could hope to optimize for, say, a weaker notion of regret, such as Stackelberg regret, which basically compares the optimal thing, or compares what you did to the optimal thing given that agents strategize, whereas strategic regret compares it to the optimal thing given that agents don't strategize. So I guess that's all I had. I guess we have plenty of time for questions. And yeah, thanks.
Are there questions for Keegan? Thanks for the great talk, by the way.
Yeah, for sure.
Maybe not a question, but like just a quick like a remark or comment, and like going back to you, Aaron's question about the greedy algorithm. I do think it's actually kind of interesting that like you are in this kind of like strategic settings in which things could really go out of hand pretty fast, but you actually do something that's very simple and like you don't really have to, I mean, it's not. I'm not trying to undersell the algorithm. I'm just saying like the fact that it's kind of like a greedy, simple algorithm and it actually seems to work and actually to low regret in this kind of setting is actually super interesting. In general, shows that you don't necessarily have to do something super complicated and you can do something that's kind of like simpler and interpretable in that sense. And I found that to be very nice.
Cool. Yeah, thanks. Yeah, that's a good point. And I guess that's also sort of why I like the algorithm, because it's quite similar to what you would do, I think, in practice if you're deploying such an algorithm. What you would do is you would keep track of like this best machine learning model you have so far, and you would only train it on data which you are like pretty sure has not been strategically modified. So yeah.